class. Today we will jump into Chapter 5, Number Theory and the Real Number System. We will be looking at prime and composite numbers today. Our objectives will be to determine divisibility, write the prime factorization of a composite number, find the greatest common divisor of two numbers, solve problems using the greatest common divisor, find the least common multiple of two numbers, and solve problems using the least common multiple. Now, number theory and divisibility. Number theory is primarily concerned with the properties of numbers used for counting, namely 1, 2, 3, 4, 5, and so on. The set of natural numbers is given by the set here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Natural numbers that are multiplied together are called the factors of the resulting product. So, the factors of 24 are represented by 2 and 12, 3 and 8, 6 and 4. Can we think of any other factors of 24? Another factor of 24 that I can think of is 1 and 24. Each number has a factor of itself in 1. If A and B are natural numbers, A is divisible by B if the operation of dividing A by B leaves the remainder of 0. This is the same as saying B is the divisor of A, or B divides A. All three statements are symbolized by writing B divides A. So B with a vertical line, then A means B divides A. We write 24-12 because 12 divides 24. So remember, this symbol means divide. So anytime you see this, B divides A, 12 divides 24. Because 12 divides 24, or 24 divided by 12, leaves a remainder of 0. Thus 24 is divisible by 12. If we write 13 divides 24, so 13 divides 24, this means 13 divides 24, or 24 divided by 13 leaves a remainder of 0. But this is not true, because 13 does not divide 24. If you did try to divide 13 into 24, it would indeed leave a remainder. Therefore, we indicate that this is not true. Now we have some rules of divisibility. Let's look at divisible by 2. In order for something to be divisible by 2, we can test it. The test is the last digit 0, 2, 4, 6, or 8? If so, then that number is going to be divisible by 2. So, 5,892,796 is divisible by 2 because the last digit is 6. All even numbers are divisible by 2. The rule for divisibility by 3 is the sum of the digits is divisible by 3. If the sum of the digits is divisible by 3, then the number itself is divisible by 3. So 52,341 is divisible by 3 because the sum of the digits, 5 plus 2 plus 3 plus 4 plus 1, is 15, and 15 is divisible by 3. Therefore, the overall number, 52,341, is also divisible by 3. Divisible by 4, the last two digits form a number that is divisible by 4. So, 3,947,136 is divisible by 4 because 36, the last two numbers in this big number, is divisible by 4. Therefore, 3,947,136 is also divisible by 4. The number ends in a 0 or 5 means that it is divisible by 5. So, 28,160 and 72,805 end in 0 and 5 respectively. Therefore, they are both divisible by 5. Any number that ends in a 0 or 5 is divisible by 5. Divisibility by 6. The number is divisible by both 2 and 3. In other words, the number is even and the sum of its digits are divisible by 3. So 954 is divisible by 2 because it ends in the 4. And 954 is also divisible by 3 because its digit sum is 18. 9 plus 5 plus 4 sums to 18, which is divisible by 3. So because 954 is divisible by both 2 and 3, it is therefore divisible by 6. This should make sense because 2 times 3 is 6. So if it meets both of the 2 and the 3 criteria, it is then divisible by 6. Divisible by 8. The last 3 digits form a number that is divisible by 8. So if we look at 593,777,832, that is divisible by 8 because 832 is divisible by 8. So with 4, we had to look at the last 2 numbers. With 8, we had to look at the last 3 numbers. And if those last 3 numbers are divisible by 8, then the entire number itself is divisible by 8. 9. The sum of the digits is divisible by 9. So in order for a number to be divisible by 9, the sum of its digits must be divisible by 9. So 5,346 is divisible by 9 because the sum of the digits, 18, is divisible by 9. Where did the 18 come from? We sum the digits. 5 plus 3 plus 4 plus 6 equals 18. Since 18 is divisible by 9, the overall number, 5,346, is also divisible by 9. Those are your divisibility rules. Let's add 10 and 12 as well. In order to be divisible by 10, the last digit has to be 0. So 998,746,250 is divisible by 10 because the number ends in 0. Any number that ends in 0 is therefore divisible by 10. And we also have a divisibility rule for 12. If the number is divisible by both 3 and 4, in other words, the sum of the digits is divisible by 3, and the last 2 digits form a number divisible by 4, then that overall number is divisible by 12. If we look at 614,608,176, we can see that that is divisible by 3 because if we sum all those numbers, 6 plus 1 plus 4 plus 6 plus 0 plus 8 plus 1 plus 7 plus 6, that digit sum is 39. And 39 is divisible by 3. So this overall number, 614,608,176, is divisible by 3. And it is also divisible by 4 because the last 2 digits form a 76 right there at the end of the number. And that 76 itself is divisible by 4. So because 614,608,176 is divisible by both 3 and 4, it is divisible by 12. Let's look at the prime factorization of a number. A prime number is a natural number greater than 1 that has only itself and 1 as factors. A composite number is a natural number greater than 1 that is divisible by a number other than itself and 1. If we look at the fundamental theorem of arithmetic, every composite number can be expressed as a product of prime numbers in one and only one way. One method used to find prime factorization of a composite number is called a factor tree. So if we look at finding the prime factorization of 700, we can start with any 2 numbers whose product is 700, such as 7 and 10. And we can use what is called a factor tree to continue factoring down until we have just prime numbers. So as you can see here, we have broken 700 up into 7 and 100. 7 is a prime number. So I do not need to continue branching here because the only factors of 7 are 1 in itself. And we do not break something down that is itself a prime number. But 100 is a composite number. It has factors that are not just 1 in itself. For instance here, 2 and 50. 2 itself is a prime number. 50 can continue to be broken down. 50 can then be broken down into 2 and 25. 2 is a prime number. And then 25 can continue to be broken down into a 5 and a 5. So, if we're looking at this, the prime factorization here is just the makeup of all the prime numbers that make up 700. So we have a 7. Ooh. So we have a 7, a 2, a 2, a 5, and a 5. That makes up our 700. Now, if we write this out, it says, thus the prime factorization of 700 is 700 equals 7 times 2 times 2 times 5 times 5, like what I wrote on the previous screen. If we want to, instead of writing each number multiple times, we can use our exponents here. So we have 7 times 2 squared times 5 squared. Using the squared because we had 2 2's and 2 5's. And typically in a standard form, we write the smallest number first and work to the largest number. So in a standard form, we would write 2 squared times 5 squared times 7. Notice we rewrite the prime factorization using a dot to indicate multiplication and arranging the factors from least to greatest. Now, to find the greatest common divisor of two or more numbers, we need to write the prime factorization of each number, select each prime factor with the smallest exponent that is common to each of the prime factorizations, form the product of the numbers from step 2. The greatest common divisor is the product of these factors. Pairs of numbers that have 1 as their greatest common divisor are called relatively prime. For example, the greatest common divisor of 5 and 26 is 1. Thus, 5 and 26 are relatively prime. So, let's find the greatest common divisor. So, finding the greatest common divisor of 216 and 234. What we need to first do is write the prime factorization of each number. So, we need to break down 216 and break down 234. Here, we've broken down 216 by first dividing by 2. If you do not know what something divides into and you don't know the factors of something, it's always easiest to start with 2 or 3 to see if those two numbers go into the overall number, and then just slowly work down, because 2 and 3 go into many, many numbers. Now, 2 goes into 216 108 times. That 108 can further be broken down into 2 times 54. That 54 can further be broken down into 2 times 27. That 27 can be broken down further into 3 times 9. And that 9 can be broken down into 3 times 3. And now we have it completely broken down into prime numbers. The 234 can be broken down into 2 times 117. The 117 can then further be broken down into 3 and 39. And the 39 can be broken down into 3 and 13. Now, this is where our division rules come into effect, because knowing our division rules can help us figure out what to divide into these numbers to break them further down into their prime. So if you need to revert back to that division table earlier in the lecture, the rules of divisibility table, please do so as you work through these examples and the homework. Now, after we have written the prime factorization of each number, what we need to do is actually write it out here with our exponents. So if we go back here, we can see that 216 equals 2 to the third times 3 to the third, and 234 equals 2 times 3 squared. All we had to do to get those was count the number of 2's here. In this one, we had 3. Count the number of 3's that we had in this one. We had 3. And this one, we had 1 2. We had 2 3's. And we had a 13. So, those are the factorizations here. So, as you can see, 216 was 2 to the third times 3 to the third. 234 was 2 times 3 squared times 13. Now, step 2, we need to select each prime factor with the smallest exponent that is common to each of the prime factorizations. And then, once we do that, so we will select each prime factor with the smallest exponent that is common. It has to be common, which means it has to be in both of each factorization. So, what do we have in common here? We do have a 2 in common, and the smallest exponent on that 2 is the 1. The 1 is imaginary there. It's just hiding up there. We don't necessarily write 1 exponents, but there is a 1 up there. And then we also have a 3 in common, and the smallest one of those is the 2 exponent. So we'll write that. So the next part says which exponent is appropriate for 2 and 3, because that is what is in common. We chose the smallest exponent for 2, so that's why we took 2 to the first power. And for 3, we took 3 to the second power. So 2 is a prime number common to both factorizations, and 3 is a prime number common to both factorizations. And now, step 3, we form the product of the numbers from step 2. The greatest common divisor is the product of these factors. So the greatest common divisor here is 2 times 3 squared. And if we actually solve that out to be the number, that's 2 times 9, which is 18. Therefore, the greatest common factor, or greatest common divisor, you can use those terms interchangeably. Greatest common divisor and greatest common factor mean essentially the same thing. So the greatest common factor for 216 and 234 is 18. Now we can also look at the least common multiple of 2 or more natural numbers. And that least common multiple is the smallest natural number that is divisible by all of the numbers. To find the least common multiple using prime factorization of 2 or more numbers, we will first write the prime factorization of each number. Second, we will select each prime factor that occurs raised to the greatest power, in this case, to which it occurs in those factorizations. And then we will form the product of the numbers from step 2. The least common multiple is the product of these factors. So let's do an example. Let's find the least common multiple of 144 and 300. Step 1, we need to write the prime factorization of each number. Now, you can do your factor tree and break these down however you would like. If we need extra practice, we can do that. We can come over here. We can say 144 breaks down into 12 times 12. 12 breaks down into 2 times 6. 6 breaks down into 3 and 2. Going to break these down as well. Oops. And what we can see here is we have, where'd it go? 1, 2. So 1, 2, 3, 4 2s, and 3, 3. So 2 3s. We can also break 300 down if we would like. I'm going to break that down into 3 and 100. So there's our 1 3 there. I'm going to break that down into 25 and 4. The 4 breaks down into our 2 2s. The 25 breaks down into our 2 5s. And here is the prime factorization of each. So the 144 was 2 to the 4th times 3 squared. The 300 was the 2 squared times 3 times 5 squared. Now, step 2, we need to select every prime factor that occurs raised to the greatest power to which it occurs in these factorizations. So if we look at 144 and 300, they both have 2's in them, but we need to select the one with the greatest power. That's the 2 to the 4th. They both have 3's in common, and we need to choose the one with the greatest exponent here. That is 3 squared. Now they don't have to have it in common in order for it to be selected, because we want to select every prime. Every prime. So we're also going to select this 5 here. Even though it's not common, we're selecting every prime and choosing it to the greatest factor. So here it's to a squared. We're going to select that. So we basically wind up with 2 to the 4th times 3 squared times 5 squared. We want to form the product of the numbers from step 2. The least common multiple is the product of these factors. So 2 to the 4th is 16. 3 squared is 9. 5 squared is 25. If we multiply all 3 numbers of those together, we get the least common multiple, which is actually 3,600. The least common multiple of 144 and 300 is 3,600. Thus, the smallest natural number divisible by both 144 and 300 is 3,600. Let's do another example. Solving a problem using the least common multiple. A movie theater runs its films continuously. One movie runs for 80 minutes. A second runs for 120 minutes. Both movies begin at 4 p.m. When will the movies begin again at the same time? Solution. We are asked to find when the movies will begin again at the same time. Therefore, essentially, we are looking for the least common multiple of 80 and 120. Let's find the least common multiple, and then we can add this number of minutes to 4 p.m. and find when these films will be ran again. So, our factorization, our prime factorization of each of these numbers is given here. Let's go ahead and just double check how those were found. I'm going to break 80 down into 8 and 10. I'm going to break 10 down into 2 and 5. I'm going to break 8 down into 4 and 2. And I'm going to further break that 4 down into 2 and 2. So what we can see is here is our prime factorization of 80 is 2 times 2 times 2 times 2, which is 2 to the 4th, times 5. We can also break down this 120. I'm going to break that down into 12 and 10. The 10 I'm going to break down into 2 and 5. The 12 I'm going to break down into 4 and 3. And the 4 I'm going to break down into 2 and 2. So here we can see we have 3 of these 2's, so 2 to the 3rd. We have a 3 and a 5. Now we need to select each prime factor with the greatest exponent from each factorization. So we are going to select the 2 here to the 4th, because that is the highest exponent. We are going to select the 3 here, and we're also going to select the 5. Doesn't matter which one, because they're both to the same exponent. And this is our LCM. 2 to the 4th times 3 times 5. So that is 16 times 3 times 5, which is 240. Therefore, it will take 240 minutes or 4 hours for the movies to begin again at the same time. Now, if you're questioning how we got the 4 hours from the 240 minutes, 240 minutes, if we change that and convert it into hours, in order to do so, we need to divide by 60. Because there are 60 minutes in 1 hour. And we're basically doing a conversion factor here. And when we do that conversion, we see that, hey, that equals 4 hours. So if we add 4 hours to 4 p.m., they will start again together now at 8 p.m. I hope this was helpful. I hope you enjoyed the lecture and learned something. Please attempt your homework. If you have any questions whatsoever, do not hesitate to reach out. Y'all have a great afternoon.